Good morning. So, who remembers the Geico commercial with the camel walking through the office? Anybody? Yeah, it's Hump Day, right? So this is Hump Week. You know that, right? It was the middle of the term, and so what I love about because it's Wednesday all week long. Didn't you know that? This is a national holiday. It's Wednesday week. So here's the thing. So people lament Hump Day, right? People lament Wednesday because they got what? How many more days till the weekend? 2.5 days till the weekend, depending on when the weekend starts, right? So people lament, but if you think about it this way, you're sitting, I mean, this will be tomorrow. Oh, tomorrow would be a lecture to not be away from. You want to be here tomorrow for lecture. Tomorrow's going to be memorable. Not like blonde wig memorable, but it'll be memorable. So when you're sitting on Hump Day, you're sitting in the middle of the week, right? That means you can look back on the week that was, and you can look forward on the week yet to be, and do all the stuff that you were supposed to already have done. So my favorite part about Fridays is that there are 2 working days left before Monday. All right. Anyway, so this week we're gonna talk about modeling manufacturing processes. As engineers, why do we want to model manufacturing processes? Go ahead. Because it's cheaper than doing them not modeled. Oops, that's not the one. Which one do I want? That kind of was the one I wanted. There. I guess that's more the one I want. So prior sets, I remembered, see? Is it written on your shirt?
Yes, it is.
It is.
WPI stands for Waskin per iron.
Wow. Have you ever talked to anybody about this? Therapist, anything like that? Because anyway. It's actually cool to have a thing, right? Yeah. No, but it's cool it's cool that he's proud of his name. I think that's cool. And one of these days I'll tell you about Heroin Kid. But so we do, prior is correct. We do modeling in any situation. Prior is correct. He was correct. Prior was correct. In any situation, we do modeling so that so that we don't have to waste time doing the actual thing, right? I mean, I guess there is the situation where we're doing modeling, like who used to build like model airplanes or whatever when they were a kid? You smell the glue when you're gluing the stuff together. Anybody? 1, 2, really not more than that? Everybody got one as a gift though as a kid, right? Everybody got one as a gift because there's always an uncle that's like, this kid's going to be an engineer. This kid needs a model airplane, right? There's always that uncle. Anyway, so that is kind of like modeling, but that's not the kind of modeling we're talking about. And anybody, actually, this could happen. Anybody was a model on the runway? Anybody here? Could have happened, but I don't know. My aunt was a model, like a runway model. And then she became an accountant for the designer that she was modeling for, which I think paid certainly longer term. Anyways, go.
Would you mind turning off the audio on the video?
I removed the video from the stream, I thought.
Supposedly.
I believe.
Exactly. Zarian says it's loud. So I'm going to have to take his word for this one.
Zach, is that better? Thumbs up. But really, I'd like clicked the button that said remove from stream. I think that maybe the audio was loud before I removed it from the stream. All right, so we do modeling because it's cheaper than doing the real thing, right? We could do the experiment, we could do the model. What kind of models are there? There's physical models, like the model airplane that we built. There's also mathematical models. Is that true? Which kind do you think we're going to make here? Really? Pretty sure we're going to do the mathematical one in the classroom. We will, however, use some physical models tomorrow. Oh, did I mention you should be in class tomorrow? It'll be a fun class to be at tomorrow. We will use some physical models tomorrow, but in general, we're going to use mathematical models. Now, as a manufacturing engineer, if we're looking at, and let's use CNC machining as our process example. You can apply this idea, this technology, these thoughts to any manufacturing process. All manufacturing processes do something physical to something to add value to it so that it's worth more and that our customers buy it. So you can use modeling to simulate any manufacturing process. We're going to use CNC machining. So if we're going to model CNC machining, what answers might we want to have without having to do the experiment? Because we could always do the experiment, right? We could do the experiment, collect the data. We're trying to skip part of that process. What questions might we want answered if we're going to do this? Yes?
Is my toolpath correct?
By correct, what do you mean?
As in, does the toolpath that I have given lead to the part that I want?
So does the toolpath that I programmed actually result in the part that I want happening. All right. And every time in the CAM software, you click the simulate button, you're actually modeling that toolpath. You're seeing, does the toolpath move the tool in a fashion that it would make the part? So we can model toolpaths. Now, if we didn't have the CAM software, could we still model a toolpath? Of course we could, but it would be harder than just pressing the play button, right? But we could do the math. We could draw on a piece of graph paper the spot where the tool is going to go for each thing around the toolpath, right? So we could totally do that. All right, so we're going to model toolpaths. The tool we like to use for that is a CAM software because it just sort of, we press the button, it does it for us. What else as a manufacturer? And this is a good one because if you can't actually make the part, like if you don't have a toolpath that makes the geometry you want, customer's not going to pay for it. What else might we want to model as a manufacturing engineer? What might we want to know before we actually start cutting material? Yeah.
Maybe like the final weight of whatever you're making.
So we might want to know what the mass of the part is, things like that. That really, that's kind of the designer's job, unless it impacts our ability to move the part around the factory while we're making it. So we might want to know that, but that's really kind of the designer's job. The designer picks those things. As the manufacturing engineer, what might we want to model? So can we, yeah.
Cycle time?
So we might want to understand cycle time. I got to find out where that good chalk came from and get some more of that. We might want to figure out cycle time. Again, we could use the CAM software for that. It actually, I don't know if you've gotten to this yet in going through the tutorials and stuff, but when you select a cutting operation, if you go to the properties, it'll tell you how much time it's going to take for that. And so they know that because they know the feed rate that you selected, and they know the distance that it has to travel at that feed rate. So it's easy for the software to calculate that. You could also model it, on your own. So we might want to know cycle time. Again, the CAM software is going to do that. If this lecture wouldn't be nearly as exciting, actually, it doesn't seem like it's that exciting for you guys. Everybody stand up. Turn around one time. All right, put your left foot in. No, sit back down. Sit down. I'm trying to wake you up. This is, I don't get it. I mean, it is hump day. I mean, hump week. That sounds just weird. I should probably stop saying that. It's hump week. But it is the middle of the term. Everybody's sort of either overwhelmed or underwhelmed with all their classes. And it's hard to pay attention. But by the way, you should be here tomorrow. Tomorrow's going to be good. I also note that week 3 is the week that people stop coming to lecture, especially when they're video, right? Because you could always watch it later. And later, you could play it at 2x speed, right? So it's like me doing this instead of me doing this. So you could do that. Anyway, so this lecture would be pretty boring if everything we're going to model we could do by pressing play in the simulate in the CAM software. What else might we want to model? As a manufacturing engineer, what do we want to know before we get a tool path? We've got to decide what machine tool to use, right? So what are some things we might want to model about our process before we even pick which machine tool?
Like tool geometry, like which tool would fit in this.
All right, so that's a thing. And so when we talk about design for manufacturability, which we're going to do like week 5 or 6, we talk about that. At that point, we're going to stress, does the tool actually fit in the geometry you want to make? But that's really a toolpath thing, right? You can't make the part if the tool doesn't fit in there. So yeah, what else though? Yes. So the material selection for the workpiece itself is chosen by the designer, but knowing what that material is going to help us figure out one of the things that we almost always want to know before we pick the machine. In fact, you could pick the machine without knowing this, but it's, you know, it's like flipping a coin. So I mean, we do model the workpiece to try to figure out, yeah, but the designer does that. Yeah, but I agree. We do have a model of the workpiece in order to know, is this the shape we want? But what is it we as manufacturing engineers want to know? So how will that material respond to the machine and to the machining process we're doing on it, right? And so, for example, that's weird. Okay. I thought we were going live. I could hear it on YouTube, but apparently it didn't work on Facebook. Oh, well. So when we're doing this, the material is important because it's going to determine what happens when we let that tool path go. So what does a tool path include? What are the parameters that are included in a tool path? So position, so the position that we move to and from. What else does it include? What do you have to have in order to decide the path the tool's going to go through? What are the process variables we get to pick? So we get to pick the feed, the speed, and the depth of cut. Yep.
We get to choose which tool we're using.
We get to choose the tool geometry. We get to choose the feed speed, depth of cut. We get to choose the tool geometry. The material that the part's made out of is important. We don't get to choose it. The designer has to choose that. But it's certainly going to be important. If we know the feed speed, depth of cut, we know the tool geometry. So, yeah, I have an example here. I have a tool here, right? I'm going to use the tool to do work on the chalkboard with a feed speed and depth of cut. Now, I'm going to do it again with a different feed speed depth of cut. Shit. Let me try again. That must be a fluke. I'm going to do it again with that feed speed depth of cut. Damn it. All right, let's try again. No, they don't buy the chalk. I have no idea who buys the chalk. You guys bought the chalk. Thank you.
Yeah.
Did you learn from that lesson? So what might we want to understand that we could model knowing feed speed, depth of cut, tool geometry? Because if it was that big fat piece of chalk, I don't think it would have worked. I don't think I could have pressed hard enough. Well, so we actually pick the tool strength when we pick the geometry and the material the tool's made out of. So we're not going to model that. We're going to pick that. So we've got the independent variables. Those are the things we pick, right? The feed speed, depth of cut. What are the dependent variables that we might care about? Well, what's the force acting on the tool, right? The chalk broke because it was too much force, right? Well, the tool breaks when there's too much force. So we might want to understand how much force, because when that tool, right, we drew our picture last time of the cutting tool and our workpiece. And there's chip going up this direction, right? So the cutting tool's moving through the workpiece. That's moving through the workpiece. Well, what do we know about how it's moving through the workpiece? We know about the speed at which it's moving through the workpiece, right? So we know the speed that this is moving through the workpiece. What are the units for speed? Velocity? Because engineering is math, right? Just a bunch of word problems, cancel the units. So what are the units for velocity? Distance over time. So distance over time is our velocity. Now, is distance over time going to tell us if the part breaks? Probably not. What are the units? So we said it was too much force that makes the part break. So what are the units for force? We'll say newtons. So we've got newtons. And so if this is distance over time and we're using newtons, what units should we use over here? Yeah. For distance over time? So we could do like meters per second. Right? If we know meters per second, we want to know newtons. What else do we have to know? So we are going to want to know the volumetric material removal rate. And for some amazing reason, we call this Q. And this is volumetric So MRR, material removal rate, Q. So we're definitely going to want to know that. But what's the relationship? All right, so these are newtons. These are meters per second. What's a newton meter per second? A joule? Is it a joule is a newton meter per second? So it's a kilogram meter squared per second squared is a joule. Right, so that's a joule. So what if we just take meters per second out of this? Right, and so then we have meters per second times and so what's this again? I wrote my equation wrong. I'm just going to put the slide up. So much more fun when I do it on the board. So energy is joules. So energy is joules, and it's the ability to do work. Work is force times distance. It's also the units for power. So we're doing our machining operation. If we know how much power the machining operation takes, and we know how fast we're moving the tool through the workpiece, we can know what the force is going to be. Does that make sense? So if we're doing a machine, so let's say we're doing an experiment. if we're doing a machining operation and we want to know how much power it's using, what would we do? So we had electricity coming in the back of the machine tool. We got work pieces coming in the front of the machine tool. We have a tool path that moves the cutting tool through the workpiece material. If we want to know how much power that's using, what would we do? Any double E's in the room? I already asked this question, right? If I want to know how much power something's consuming, what do I do? What do I need to know how much power something's consuming? Voltage and current, right? So we could do that. We could actually measure that. We go back to that video that was too loud. This one. Let's look at the loud video. I'll try to talk louder. So when you're at the machine tool, you can see that there's a meter that's telling you how much power is being used by the machine at this moment. So as we go through, what we're changing here, so what we've kept the same is what tool is it? The tool geometry is the same. The tool material is the same. Keep an eye on that spindle load meter. So where was it for the first pass? About right about actually where it is right now, where I stopped it, huh? Because it was just leaving the part. Let's look at this first pass. So it's about halfway between 0 and 50%, turns out. Then we do the second pass here. It's about halfway between 50%, maybe a third of the way between 50% and 100%. And with this third pass, it's up at about 150%. And so that was the power consumed by the machine tool to spin that cutting tool as it was feeding through the workpiece material. The only thing that changed between the three operations was the incremental depth. That axial depth of cut was increased between those three operations. And so you can imagine, and if the people at home heard this, and if we didn't have so much feedback here, you guys could have heard it too. But when you do get home, click on the lecture notes and listen to that video. What you would have seen or heard is, yeah, go ahead.
So is that electrical power?
That's electrical power that's going to the machine. Yeah. That's really easy for us to measure because we have a voltmeter and an amp meter, right? So we can measure the electrical power that's going to the machine at the moment when we're cutting. Super easy to measure. But it's exactly the same minus some losses, right? So there's going to be some losses between the motor and the cutting edge of the tool. What things would get lost there? There's friction in the spindle, right? We can actually figure out what that friction in the spindle is by spinning the tool without cutting and looking at what that nominal value is. So you could actually zero that part of it out. But there are some losses in that transmission. But yeah, it's a linear relationship as it goes through there. So that power is going to depend on the workpiece material. So if you were going to cut aluminum or stainless steel, which one's easier to cut? Is there anybody that thinks stainless steel is easier to cut? Well, I used to think that it was aluminum too. I mean, for years, I thought aluminum was easier to cut than stainless steel. Until I realized that for me, as the manufacturing engineer, all I had to do was tell the computer which one it was. So for me, it was exactly the same effort level. But that stainless steel takes 7 times as much energy as the aluminum does. It takes 7 times as much power to cut the stainless steel part as it does to cut the aluminum part. So there is a difference between them, but easier, harder, I don't know. All right, so we need to know the workpiece material. Yeah.
Isn't it still like kind of harder though, because you have to buy specialty bits for cutting steel and you have to like reduce your speed. So, like,
Again, which one I buy isn't harder. Knowing which one it is, it freaks with the mind sometimes. Because I mean, for years, and if I was, using a plane and doing it by hand, then I would probably say it still is harder to cut the stainless steel, because I would have to do that for longer while cutting it. But if I'm just programming the computer to program the machine tool to go do that. Now you have to take different things in consideration. So if we've got more power going to it, we're going to have more force, right? Which means we may have to change our cutting parameters. So we may have to, how do you think intuitively, how do you think we would reduce the cutting force? Because we don't get to pick the material, the designer picks it, right? So you could move the tool slower through the material. You could have less axial depth, or you could have less radial depth. And what you're doing is all three of those situations, you're reducing the volumetric material removal rate. So if you reduce Q, power is going to go down, force is going to go down. All right, so besides material removal rate and what material we're cutting, what other parameters do you think impact how much power it takes? Yeah. How old or new the machine is will definitely impact that, how much is lost between the spindle motor and the cutting edges of the tool. Especially if it's old and compliant and it vibrates a lot more, a lot of energy will get dissipated in that vibration. But how old or new the cutting tool is also. So every time that cutting tool moves through the workpiece material, it gets a little bit less sharp. And when it gets a little bit less sharp, it changes that geometry, and it takes just a little bit more force every time that cutting tool goes through the workpiece material. Now, luckily, with most workpiece materials and cutting tools, that happens slowly over time. Although I've had jobs where you could measure the change in size of the cutting tool for each 8 minutes of operation. And so it was a grinding job, and depending on how fast we wanted to make them. So if we want to make them faster, we have to increase Q. We increase Q by increasing feed speed, depth of cut, actually just the speed of the feed and depth of cut to do that. And if I made them, if it took 30 minutes to make one part, you couldn't measure the wheel wear on the grinding wheel. But I could also make the parts in 8 minutes without breaking anything. And in 8 minutes, it used $10 worth of grinding wheel on every part. I could measure the grinding wheel, and you also had to set it up every time, because every time you did it, the grinding wheel was a different size. So, but great quality in manufacturing is giving the customer what they need when they need it. When the customer's in a hurry, sometimes you have to spend more money to get it to them. All right, so material removal rate, the workpiece material, feed speed, depth of cut, you have to know how worn out is the tool. So we'll have a tool wear that we look at. And I'm not sharing the screen. Let's share the screen again. Share the screen, close that window, advance the slide. All right, so energy, yep. Oh, I had this cool animation. You can watch that later. Right, power is the rate at which we apply the work. We're going to use a mixture of, what do they call these imperial units? Yeah, but they went metric like over 100 years ago. We totally did. You know which countries still use these imperial units these days? There's 3 that I know of. The United States is one of them. Anybody know what the other 2 are?
Is it Australia and the Galactic Empire?
No, it's not Australia or the Galactic Empire. Sierra Leone and Myanmar. So we're in unit heaven here. By the way, how long is an inch? Yep, 25.4 millimeters. You didn't know it, but we've been using the metric system since the 1860s when Congress voted that the inch was exactly 25.4 millimeters. So we don't even use the inch standard anymore. But we like to confuse the foreigners with the math. I'm going to stick with that. That's probably the only reason we haven't gone metric yet. All right, so just make sure the units cancel. When you're doing a problem that deals with this, make sure the units cancel. If I give you horsepower, make sure you take into account that 1 horsepower is 33,000 foot-pounds per minute. Yep, and power equals force times velocity. So remember I told you the power depends on material removal rate, what material you're cutting, the feed, what material you're cutting, how sharp the tool is. That's pretty much what it depends on. It actually, there's a little fudge factor we put in. When you make a model, who's made a mathematical model for class before? Really? You must have. All right. When you make a model, how do you know your model's any good?
Because it reflects what actually happens.
I mean, when I make a model, it's because I'm wicked smart. But when you make a model, what you're going to want to do is you're going to want to test the model, right? So you have to do an experiment to validate the model. And when you consistently find that your model's sort of right, but it's a little bit off to the side, what do? How do you fix the model? You add what we call a fudge factor in engineering. We just make up a number that fills that place that shifts us back to where we thought we were supposed to be. And so if we go through this, oh, wrong one. Yeah, we got this part. Yeah, we did that. Looked at that. All right. So to do these kind of estimates, we're going to use the machinery's handbook. You can get it from the library, which is why I didn't make you buy the $160 book, because you can get it from the library. There's a little video here, I think. It was a video that shows you how to get it from the library. No, it's electronic, so everybody can look at it at once. And there's a little video here that shows you how to get access to it. The example in my slides here is from the 28th edition of the book. I think the 31st or the 32nd edition is the most currently published edition of the book. This math hasn't changed. You can use the 28th edition. In fact, I think the oldest one I have is the 7th edition on a bookshelf in my office. This math hasn't changed going back that far because it's physics, right? Now, the quantity of information may have changed since then. So what they've done is they've told us that we need to know about the material. And they've gone and done a whole bunch of tests with a whole bunch of different materials. And they've told us what the factor is to use depending on which material we have. So if we know that we have aluminum, we know that this is our specific power for cutting for aluminum. Now, here's our fudge factor, this feed factor. Depending on what your feed in inches per tooth is, you're either going to be a little bit less than what you wanted or a little bit more than what you wanted, but you can plug this in. The material removal rate, we talked about this. The tool wear factor. And so depending on what type of machining you're doing, so they've done thousands, probably tens of thousands, maybe hundreds of thousands of experiments to build up this database that we're going to get for free. Well, it's not really free, right? It costs you like $65,000, but it's included with your tuition. from the Gordon library. Depending on what operation you're doing, if the tool is sharp, use a factor of 1. If the tool is not sharp, how do you know? How do you know if the tool is sharp or not? You could touch it, be careful. It kind of depends on why you want to do the estimate. Just assume the worst case scenario for the thing you're trying to look up. If you notice that the tools are breaking, it may be because they're breaking because they're becoming not sharp. Because when they become not sharp, the power goes up, the force goes up. Right? So assume the worst case. So you can get the power of cutting by multiplying that KP factor by C, by the fudge factor, by the material removal rate, volumetric material removal rate, by this tool wear factor. When you go to the machinery's handbook, there's going to be a KP to use if you're using metric units. There's going to be a KP to use if you're using imperial units. Make sure you use the right one. If we have some really bad quiz questions that mix the units. So I'll give you like inches and kilograms. It's really because I'm an idiot, not because I was trying to be a pain in the ass. But I went with it because engineers should be able to figure out what the units are. So pay attention to the units. I tried to fix all those, but I'm sure some of them have slipped through. You have to use the machinery's handbook to know what these numbers are, except for the few of them for some of the questions that you could pick off these slides in this presentation. So what you'll note in this equation is it doesn't say speed, right? There's no velocity. Now the Q involves the feed rate and the depth of cut and the width of cut. It doesn't involve the speed. Those are independent. You get to pick both of those when you're setting up the thing. But didn't we say at the beginning that power equals force times velocity? And we also picked the velocity, right? We picked that surface speed. The surface speed, again, is the speed the edge of the tool moves through the workpiece material. So we picked that too. So you can work either direction on this problem. You could estimate it by looking up the values of the machinery's handbook, or you could use knowing that force equals power equals force times velocity. You could use that to figure out what numbers to put in the table in the machinery's handbook by doing your experiment. So you can run this both directions. And remembering those two facts is going to get you through most of the mathy part of this class. Most of the mathy part of this class happens this week. And then we'll talk about it again later in the term, but most of it happens this week. And it's really simple stuff like this. So power equals force times velocity. Power also equals Kp times C times Q times W. But that's the power at the cutting edge. What do you think we add to this to get the power at the motor? Well, to get the power at the motor, we just need an efficiency factor for that type of machine. Right? So it's just one more factor. So if we're measuring the power at the motor, like on our spindle meter on the mini mill there, or if we're hooking up our scientific instruments to measure that, which is one of the most common ways to do this kind of experiment, is to just inductively measure the current and the voltage that's going to that motor. You need to know how much of that power gets transferred to the cutting tool. All right, so we want to do this. We want to build this kind of a model so that we can understand how much power it's going to take to do the cut, because we'd really like to know how much force we're going to put on the workpiece. So what's the force going to be between the workpiece and the tool, right? So if we know what the force between the workpiece and the tool is, how do we use that knowledge? Yes. Okay, so what increases the strength of a tool? So if we know we're going to have a higher power, we know we're going to need a stronger tool. So what about a tool would make it stronger? Yes. So more diameter, more strong. More diameter can't fit into small radiuses though, right? All right, so more diameter, more strong. What else would make the tool stronger? So there's coatings that we put on the tools, and typically those coatings are there to make them harder and have less friction. But I think it could, I'm willing to believe that it could add some strength. But yeah, the coating, but the reducing friction makes the force go down, so you don't need as much strength, right? So that's why we do the coatings. Yeah.
The material inside the coating.
So the material the tool is made out of is going to have a big impact. So the geometry and the material of the tool. Who was in lab this morning when the tool broke? You were? Yeah. Do you know why it broke?
Nobody knows.
Oh, I knew why it broke. When they told me it broke, I told them why it broke and how to fix it. There should have been somebody working on fixing it. Maybe you'd left the area before I had the conversation. So it was a carbide drill that broke. The carbide drill broke because the force was too high. 100%. The tool broke because there was too much force. Every time when the tool breaks, it's too much force. In this case, there was too much force because the setup was wrong and it wasn't actually in the center of the workpiece. And so instead of drilling a hole, which it was designed to do, it was trying to sort of kind of like mill the hole, but it wasn't designed to do that. And so there's just too much sideways cutting force on it. I think they've fixed it by now. Were you there for the second drill that broke or the first one?
The second one.
For the second one, yeah. Remember, if you keep doing the same thing again, the tool's going to break the same way again. All right, so we could have fixed that by actually setting it up correctly and having the drill go in the center of the workpiece. We could also have fixed it by getting a bigger drill. A bigger drill would have survived that no problem. We also could have fixed it by getting a more ductile drill. If we allowed the drill to bend, it would have made a hole. The hole wouldn't have been in the center of the part. And the hole would have been a little bit curvy as it went through the part. That's not the ideal solution. We actually use the carbide drills for that operation because when we use bendy drills, when we use steel drills, they do bend. And the hole starts in the center of the part, but never comes out in the center of the part because it bends the part, bends the tool. All right, so we could make it stronger by getting a stronger material, by getting a thicker material, by getting a bigger diameter end mill. What else could we do if we had to say that same diameter? What could we do to make the tool stronger, do you think? We could reduce the force by reducing the cutting parameters, right? But if we don't want to do that and we want to make the tool stronger, so you'll notice when you see the even drills and end mills and things, you'll notice they have different numbers of cutting edges on them. So the drill, as an end mill that has more flutes, more cutting edges, is going to actually have more core material also. One with fewer cutting edges is going to have less core material. So in effect, we're making it thicker by putting more flutes on it. Now, what's the problem with putting more flutes on it? The reason for the flutes, the gap in between the cutting edges, is so that the chips have some place to go, so that the chips can leave the workspace, the cutting area. And so if we put too many flutes and we're using a material like aluminum that's got, it expands pretty quickly when it gets hot, and it's pretty hot when it's getting cut. That friction adds a lot of heat. That aluminum expands and it'll actually weld itself to the tool very quickly. That's why you tend to see us use coolant when we're cutting aluminum. Partly it's to keep the cutting edge less hot, but mostly it's to push all the chips out of the hole, so we don't recut those chips. All right, so what are the key takeaways from today's lecture? What are the things that you must, besides come tomorrow, be in class tomorrow? besides that one, what's the key takeaway from today? Sounds like a really good quiz question then. Yeah.
The formula for cutting power.
Right. So power equals, it depends on the material, the Q, the material removal rate, the tool factor, and the fudge factor, and then any efficiency between the spindle and the workpiece. What other key takeaway from today?
That you can like model a lot of these parameters without actually doing anything on the machine because of previous.
So you can actually think about it before you start doing it. You could pre-understand if the tool's going to break, or so the other reason we want to know that force is all that force is pushing on the workpiece, right? Well, we want to know how hard do we have to clamp on the workpiece to keep it from moving when we're pushing on it, right? So I think next Tuesday we talk about fixturing, and we're going to do we'll do mathy stuff about that too. But we're going to use this information we got from estimating cutting force to estimate the friction force we're going to need, because it is friction that keeps that workpiece in the fixture, almost always. So power equals this formula. Power also equals force times velocity. Those are the two key mathy takeaways that you're going to want to have. All right. Oh, and what was the most important key takeaway from today's lecture? Be in class tomorrow. And, unless you have COVID and you don't want to cough all over us, then stay home. But we'll. All right.
Any update on the lab kits?
Part of them here. Part of the material's here, so we're just handing it out to you when you get to class. The rest of it should be here last Thursday. And so as soon as it becomes last Thursday, I will let you know, and we'll actually get all the rest of the boxes over there. But we've got we're capable of breaking tools in lab today, and we've got 7 or 8 of those in stock, so we could break some more.
7 or 8 times.
Yeah.